Hi everyone, my name is Dariia Shyriaieva and I'm happy to join the IVS Symposium for the first time, at least virtually. I would like to present for you our study. It deals with spectral reflectance in certain way and context, which was lacking, in our opinion, in methods of remote sensing and habitat mapping before. So let's start. I'm a PhD student in vegetation science from Holodny Institute of Botany, Ukraine, and currently I'm on my scholarship at Masaryk University in Czech Republic. My colleague in this project, Oleh Prylutskyi, he's from Karazin Kharkiv National University, and he's also a field biologist, but with a particular interest in remote sensing and spatial data analysis. First of all, I want to tell you briefly the story of how this project started. The story began from the moment when I faced the need to do habitat mapping of the Buskygard National Park, where I have been working for 3 years. Our initial goal was to obtain a high-resolution map of habitat types for the national park territory, and we started from the field mapping and then switched to satellite imagery classification with machine learning methods. Just a few words about this territory. The national park is located in southwestern Ukraine, in southern Bukh River Valley. And this is quite unique for steppe zone territory because of diverse vegetation and flora landscapes. And natural habitats with high conservation value are mainly concentrated in river valleys in this region and surrounded by croplands. The next step was to deal with habitat classifications and define the list of habitats for the study territory. For such purposes, we used our vegetation data relevant with precise GPS locations and also mapping data for artificial habitats. Then we applied the new version of EUNIS expert system, also with some additions from the old EUNIS for non-revised habitat groups, and from the National Habitat Catalogue of Ukraine for some specific for steppe zone habitat types. So we obtained 32 habitat types, but some of them were represented by very small fragmented areas not suitable for the mapping in our scale. And the final list of habitats for the next step contained 26 habitat types. In the next step, we manually created ground truth data and prepared satellite data for further imagery classification. Using GIS, we created 693 polygons for 26 habitat types. And you can see that they are mainly concentrated in the river valley, where natural vegetation is the most diverse and well represented. As spectral data, we used Sentinel-2 atmospherically corrected surface reflectance data available through the Google Earth engine. And for classification, we used random forest classifier with 30 trees. So we are going to the next step, which is random forest classification to obtain pixel-based classified images with 10 meters resolution. But we should admit that our first results did not perfectly satisfy us. And we faced the problems of intermixed habitat types, classification errors, and so-called salt and pepper effect when surface classes intermixed even with homogeneous stands like croplands, and also the shape of confusions differed seasonally. So, and the most confused habitat types were croplands, Robinia semi-artificial forest, and also sometimes of natural grasslands. We were aware that additional parameterization or expanded ground truth data could help to improve our classification results, but the questions we asked yourself were, What if some habitats did not differ by spectral features at all? And which seasons are better for accurately distinguishing some confused habitat types? And which satellite bands are more important than others for purposes of classifying habitat types? And then we got an idea. To address those issues, we digressed a bit from our initial goal, and we turned to a new one. We decided to create a tool for rapid visual exploratory analysis of spectral reflectance for user-defined data, in our case for different habitat types. So the resulting workflow combined two different tools. The first is Google Earth Engine for obtaining and preparing satellite data, and the second is R for extraction pixel data and visualizations. As a result, using our tool, we could obtain three types of exploratory visualizations. First is the reflectance for a given habitat type or set of habitat types per satellite bands with some basic statistical summary. You can see on the graph, as an example, a set of all grassland types, which is group R in illness of studied territory. Second, we have such smooth spectral reflectance curves in a direct meaning, which means variation of surface reflectance across wavelength gradient. And the third, the violin plots of reflectance values density per band. These three visualizations helped us to understand the data better and to draw a conclusion about reflectance dynamics for given habitat types and to make the assumptions for further analysis. Now we will see how it works with defined sets of habitats. And with the first case, let's consider habitat types. Dry grasslands, wall stepping scrub, temperate thorn scrub, temrophyllous forest, and such complex habitats as wooded steppe. They all are occurring intermixed as small patches in our study region, and they are also connected by a succession of dynamics as different stages on the way from grassland through shrub to forest or back to grassland. So also there are some transitional communities between them. As you can see, both thermophilous forest and temperate thorn scrub show higher values of reflectance within the near infrared spectrum, which is bands from 6 to 8A. Then grasslands, wall scrubs, and wooded steppe during May, July. At the same time, in a red band, their value are lower than others. The physical meaning of this pattern is the accumulation of green biomass and chlorophyll, which affects the absorption within one part of the spectrum and the reflection within another. And this is what we actually call the NDVI index and its variation, since NDVI is a normalized difference between near infrared and red bands, which are band 8 and band 4 for Sentinel-2. And we can use the variation in reflectance dynamics between habitat, bands, and season to define the criteria of delimitation for such habitats. And with such tool for visualization, explanatory analysis, we can do it with a possibility of visual choice and understanding, not just use some known indexes and values. And also we can observe these patterns on the smooth reflectance curves. Similarly, we have the second case, a complex of the floodplain habitats. We can trace the dynamics of infrared reflectance during the vegetational season, starting with higher values for grassland habitats, meadows in spring, and then it is changing during the summer. And the same with reflectance curves. But the different picture we see with case 3, grasslands and rocky outcrops. As you can see, there are significant differences only for dry grasslands on deep soils, while spectral reflectance for 2 rocky habitats through the season is varying in the same manner. And that might be a reason for the steady confusion of such habitats with machine learning process using optical data only. So after all, let's draw some conclusions. We did something using our tool, but why have we come to this? Machine learning classification of remote sensing data gains popularity, but still remains a black box. Most of the reasoning we can get from machine learning methods is importance of used bands from most to least meaningful, but we delegate the decision to the machine and we have to rely on its wisdom anyway. We think that vegetation or habitat mappers need a flexible tool to explore the spectral features of the habitats or land cover classes, at least to decide which seasons and bands should be used and why. Here you can see some of the practical applications we did with our data. So we explored the variability of the spectral reflectance and across satellite bands and vegetative seasons. We identified groups of habitats that are similar in spectral reflectance characteristic, and we focused our work on them. We detected the most distinguishable satellite bands and seasons for fuzzy and intermixed habitat types. And finally, we decreased the number of satellite data used for random forest classification twice. And we had the overall classification accuracy around 94%, which is a quite high level. Our data and scripts are available as GitHub repositories through the link on the slide or QR code. And we are grateful to the National Park Buskegard and also to funds which supported some stages of our presented study, National Research Foundation of Ukraine and also Rafford Small Grant Foundation. Thank you for your attention. And in the end, we would like to ask you a few important for us questions. So what do you think? Could it be helpful? Do we need exploratory analysis before machine learning classification? How would you name this tool? Because we didn't name it before, but we want to do it before publishing it in the paper. And also welcome to improve the code. Thank you for your attention and looking forward to see your answers.